Chapter 4. In the chapter The Electric Spark, we shall study various terms related to electric current and its applications in our day-to-day life. We are dependent on electricity for almost all our activities through the day. Electricity is very important to make our life comfortable and easy. Let us do this activity. Take a torch, take out the cells and try to obtain light. Is it possible to get light? Why? No, it is not possible to get light. The cells are the source of power. Since they are removed, the torch does not have a source of power. A. Take two small copper wires, join its ends to a small bulb. Join the other two ends of a wire to a dry cell. Observe the bulb. The bulb glows as it draws power from the dry cell. B. Take out any one end of a wire connected to the cell. Observe the bulb. What do you infer? The bulb does not glow. The wire transfers the power from the cell to the bulb. When the wire is removed from one end, the flow of current is broken. Hence, the bulb stops glowing. Let us understand about electric current and circuits. In a metallic conductor, each atom has one or more than one loosely bound electrons. These loosely bound electrons are considered as free electrons. They can move from one part to another part. Since these free electrons move throughout the conductor, they are the charge carriers. Electric current is a flow of electrons in a conductor or the amount of charge flowing through a particular cross-sectional area in unit time. Current flow in a wire. If the metal wire is not connected to any cell or a battery, then the electrons present in it move randomly in all the directions between the atoms of the metal wire. When a source of electricity, like a cell or a battery, is connected between the ends of the metal wire, then an electric force acts on the free electrons present in the wire. Since electrons are negatively charged, they start moving from a negative end to positive end of the cell or battery through a wire. This flow of electrons constitutes the electric current in the wire. The electrons in the conductor move with a certain average drift speed. Actually, the drift speed of electrons for a typical copper wire carrying a small current is found to be very small. If Q be the net charge flowing through any cross-section of a conductor in time t, then current I is given by, therefore, I is equal to Q upon T. The SI unit of charge is Coulomb, C. The charge on electron is 1.6 into 10 raised to minus 19 C. The current is expressed in ampere A. 1 ampere is equal to 1 coulomb upon 1 second. 1 ampere. If 1 coulomb of charge is passing through any cross-section of a conductor in 1 second, then the amount of current flowing through it is called as 1 ampere. Small currents are expressed in terms of milliampere or microampere. 1 milliampere is equal to 10 raised to minus 3 ampere. 1 microampere is equal to 10 raised to minus 6 ampere. André Ampère, 1775 to 1836, the French mathematician and scientist, carried out important experiments on electric currents. His work enabled people to measure the amount of electric current flowing through a circuit. In recognition of his contribution, the current is measured in a unit called ampere. Now we will study electrical symbols and electrical circuits. Electric circuit, a continuous path consisting of conducting wires and other resistances between the terminals of a battery along which an electric current flows, is called a circuit. Electrical circuits are represented by drawing circuit diagrams. A diagram which indicates how different components in a circuit have been connected by using the electrical symbols for the components is called circuit diagram. Electrical symbols used in electrical circuits are given in the table 4.1. A typical electrical circuit is here. The electrons flow from negative terminal to positive terminal of the cell, but the conventional direction of current is from positive terminal to negative terminal of the cell. Let us perform this activity. Take a small torch bulb. Connect 3 cells of 1.5 volt each as shown in figure. Take 2 wires. Connect end D of wire at points A, B and C respectively and observe the bulb each time. Note down the observations. The bulb glows each time the wire is connected to the cell. Now we will study electric potential and potential difference. Is it possible that the lightning can move from ground to sky? No, but you have seen lightning move from sky to ground. Lightning is the electric discharge traveling from clouds at high potential to Earth's surface, which is at zero potential. The electric potential released in this process can be as great as 10 raised to 7 volt. Keep the water tank A at a higher level and other water tank B at a lower level. Join a pipe from tank A to tank B as shown in figure. Observe the direction of the flow of water. Water will flow from A to B, that is, from high level to low level. There are 2 conductors A and B. A is at high potential, denoted by plus sign, and B is at low potential, denoted by minus sign. If they are joined with the wire, the current will flow from conductor A to B. The current will flow from A to B till the potentials of conductor A and B become same. The current will stop flowing if the potential difference between the 2 ends of the wire becomes 0. An Italian scientist called Alessandro Volta, 1745 to 1827, invented the first battery. Volt, the unit of potential difference, is named after him. Let us see what is meant by potential difference. The potential difference between 2 points in an electric field is defined as the amount of work done in moving a unit positive charge from one point to another point. Potential difference is equal to work done upon quantity of charge transferred. V is equal to W upon Q. Electric potential is the electric level. The current will flow if there is potential difference. See these figures. In this figure, the copper wire is connected in the form of loop. No current flows through it. But as soon as this wire is connected to the ends of the battery imposes a potential difference between the end of a loop and current is set up in a loop. IV is equal to 1J upon 1C. The SI unit of potential difference is volt, denoted by V. 1 volt potential difference. The potential difference between 2 points is said to be 1 volt if 1 joule of work is done in moving 1 coulomb of electric charge from one point to another. Small voltages are measured in terms of millivolts and microvolts. Large voltages are measured in terms of kilovolts and megavolts. Students, you try out this activity and note the observations. Take a copper, aluminium and glass rod. Make the arrangement as shown using connecting wires. Place a copper rod in the gap AB. Close the key and measure the current. Replace copper rod with aluminium rod and glass rod. Measure the current each time. Note the difference. Let us perform this activity. Set up a circuit as shown. Use nichrome wire resistance R. Take 4 cells of 1.5 volt each. Nichrome is an alloy of nickel, chromium, manganese and iron. First use one cell. Note the reading in the ammeter and voltmeter. Now connect 2 cells and take the ammeter and voltmeter reading. Repeat the above steps for 3 and 4 cells in the circuit. Tabulate the result as follows and find the ratio of V and I. Till now we have studied current and potential difference. Let us find the relation between them. Electric current is the flow of electrons through a conductor. When the electrons flow from one part to the other part of conductor, they collide with other electrons and also with the atoms and ions present in the conductor. Due to these collisions, there is some obstruction or opposition to the flow of electrons through the conductor. The property of the conductor due to which it opposes flow of current through it is called resistance. It is numerically equal to the ratio of potential difference across its ends to the current flowing through it. Let us see what is meant by conductors and insulators. On the basis of resistance, substances are divided as conductors and insulators. Those substances which have very low electrical resistance are called conductors. For example, silver, copper, aluminium are good conductors. Those substances which have infinitely high electrical resistance are called insulators. Rubber, wood, glass are good insulators. Ohm's law. The electric current flowing in a metallic conductor is directly proportional to the potential difference across its terminals, provided physical conditions of the conductor such as length, area of cross-section, temperature and material remain constant. If I is the current and V is the potential difference across the ends of a conductor, then V is directly proportional to I. Therefore, V upon I is equal to R. Therefore, V is equal to IR. R is the resistance which is constant for given conductors. The SI unit of resistance is ohm. 1 ohm resistance. If 1 ampere current flows through the conductor and 1 volt potential difference is applied across it, then its resistance is 1 ohm. 1 ohm is equal to 1 volt upon 1 ampere. A German physicist, George Simon Ohm, 1787 to 1854, stated the law which is used to calculate resistance in electrical circuit. The unit of resistance, ohm, is used in his honor. Students, you try this activity and note the observations. Make the arrangement as shown. Take the wires of equal lengths and thickness made of different materials like copper, aluminium and nichrome. Join the wires one by one in gap AB. Plug the key and then calculate the resistance of each wire using Ohm's law by measuring the potential and current. What is resistivity? resistance R of a conductor depends on the length L and area of cross-section A of the conductor. R is directly proportional to L and R is inversely proportional to A. Therefore, R is equal to RHO into L upon A, where RHO is called resistivity of the conductor. It is also called as specific resistance. If we put L is equal to 1 meter and A is equal to 1 meter square, then R is equal to RHO. Thus, resistivity of a conductor is defined as the resistance of a conductor of unit length and unit area of cross-section. The SI unit of resistivity is ohm meter. Resistivity is the characteristic property of material. It is different for different materials. Table shows the resistivity of conductors, alloys and insulators at 20 degrees Celsius. Observe the figure 4.10 and answer the question. The figure shows 3 cylindrical copper conductors along with their cross-sectional areas and lengths. Compare them according to the current through them if the same potential difference V is applied across their lengths. Let us look at the activity. Take a 9-volt battery and a small torch bulb and connecting wires. Take 2 pieces of nichrome wire. Join the wires as shown and observe the intensity of the bulb. Now join the wires as shown. Observe the brightness of bulb. The bulb glows with more brightness in second arrangement than first. Let us look at the resistance of a system of resistors. In various electrical gadgets, we often use resistors in various combinations. Ohm's law can be applied to combination of resistors. There are 2 methods of joining the resistors together. They are 1. Resistors in series and 2. Resistors in parallel. Make the arrangement of resistors as shown. This figure shows an electrical circuit in which these resistors having resistances R1, R2 and R3 respectively are joined end to end. Here the resistors are said to be connected in series. In series combination, same current flows through each resistance. This figure shows a combination of resistors in which these resistors are connected together between points C and D. Here, the resistors are said to be connected in parallel. Potential difference across each resistance is same. Let us study in detail about resistors in series. As shown in the figure, suppose I is the current and V is the PD across points C and D. R1, R2 and R3 are the 3 resistors connected in series between points C and D. Then Rs is the effective resistance in a circuit and V1, V2 and V3 are the potentials across the 3 resistors such that V is equal to V1 plus V2 plus V3. Let us mark this as statement 1. But using Ohm's law, total potential difference V is equal to IRS and V1 is equal to IR1, V2 is equal to IR2 and V3 is equal to IR3. Substituting these values in equation number 1, we get IRS is equal to IR1 plus IR2 plus IR3. Therefore, Rs is equal to R1 plus R2 plus R3. For n number of resistors connected in series, we get Rs is equal to R1 plus R2 plus R3 plus R4 up to Rn. If the resistors are connected in series, then in a circuit, the current is the same in every part of the circuit. The resistance of the combination of resistors is equal to the sum of the individual resistors. The total voltage across the combination is equal to the sum of the voltage drop across the separate resistors. The effective resistance in a series combination is greater than the individual resistances. This combination is used to increase resistance in a circuit. Now let us study about resistors in parallel. Let three resistors R1, R2 and R3 be connected in parallel between points C and D. I1, I2 and I3 are the currents passing through R1, R2 and R3 respectively. Let V be the potential difference between points C and D. The current I will be given by I is equal to I1 plus I2 plus I3. Let us mark this as statement 1. Let Rp be the effective resistance in the circuit. Using Ohm's law, we get I1 is equal to V upon R1, I2 is equal to V upon R2, I3 is equal to V upon R3 and Is is equal to V upon Rp. Putting these values in equation 1, we get V upon Rp is equal to V upon R1, V upon R2, V upon R3. Therefore, 1 upon Rp is equal to 1 upon R1, 1 upon R2, 1 upon R3. For n number of resistors connected in parallel, we get 1 upon Rp is equal to 1 upon R1, 1 upon R2, up to 1 upon Rn. If the resistors are connected in parallel, then the sum of reciprocals of the individual resistance is equal to the reciprocal of equivalent resistor. The currents in various resistors are inversely proportional to the resistances. Higher the resistance, lower is the current through it. However, the total current is the sum of the currents flowing in the different branches. The voltage across each resistor is same. The effective resistance of the combination is less than the individual resistance in the combination. This combination is used to decrease resistance in the circuit. Think, in which arrangement the bulb will be brighter? Why? The bulb will be brighter in parallel arrangement. In parallel arrangement, the effective resistance is less and current more. Therefore, the bulb glows more brightly in parallel arrangement. Let us look at the heating effect of electric current. When current flows through a metallic conductor, the free electrons in the metal start moving from the end which is at the lower potential. These moving free electrons collide with the atoms of the metal. At each collision, a part of kinetic energy of electron converts into heat and slowly the temperature of the conductor begins to rise. Thus, the production of heat energy in a conductor by the electric current flowing through it is called the heating effect of the current. Let us study about Joule's law. Let V be the potential difference applied between two terminals of a conductor of resistance R. Then, by using Ohm's law, I is equal to V upon R. If the current I is passed through a conductor for time t, then Q is equal to IT. Potential difference is the work done during flow of charge Q is given by work is equal to potential difference into charge. W is equal to VQ. Put V is equal to IR and Q is equal to IT. W is equal to IR into IT. W is equal to I square RT is equal to VIT. When current flows through a conductor, the work done I square RT is converted into heat. W is equal to I square RT joule. Usually we express heat energy into calorie. The relation between joule and calorie is 4.18 joule is equal to 1 calorie. Hence, heat produced in a conductor in terms of calories is given by H is equal to I square RT upon 4.18 calories. Joule's law can be stated as the quantity of heat generated H in a conductor of resistance R when a current I flows through it for a time t is directly proportional to 1. The square of the current, 2. The resistance of the conductor, and 3. The time for which the current flows. Using Ohm's law, we can write H is equal to I square RT upon 4.18 calories is equal to V square T upon 4.18 R calories is equal to VIT upon 4.18 calories. Let us look at the applications of heating effect of electric current. In an electric circuit, the unavoidable heating can increase the temperature of the components and also alter their properties. However, heating effect of electric current has many useful applications. The most common examples are electric iron, electric toaster, electric oven, electric kettle, and electric heater. An electric bulb. An electric bulb consists of a filament. This filament becomes hot and emits light. It is made up of a metal with high melting point such as tungsten, melting point 3380 degrees Celsius. The bulbs are usually filled with chemically inactive nitrogen and argon gases which prevents their oxidation to prolong the life of a filament. An electric iron. An electric iron consists of a coil of high resistance covered by mica sheets and kept inside a heavy metal block. When electric current passes through the coil, it gets heated and can be used for ironing clothes. The mica sheet is a bad conductor of electricity and good conductor of heat. It prevents the current from entering into the metal and thus protecting the user from getting an electric shock. An important application of heating effect is the fuse used in electric circuits. It protects circuits and appliances by stopping the flow of any excess electric current. The fuse is placed in series with the device. It consists of a piece of wire made of an alloy of low melting point, for example, lead and tin. If a current larger than the specified value flows through the circuit, the temperature of the fuse wire increases. This melts the fuse wire and breaks the circuit. The fuse wire is usually enclosed in a cartridge of porcelain or similar material with metal ends. The fuses used for domestic purposes are stated as 1A, 2A, 3A, 5A, 10A, etc. In industry, soldering, welding, cutting, drilling, and working of electric furnaces are based on heating effect of electric current. In surgery, a fine heated platinum wire is used for cutting tissues much more efficiently than a knife. Let us move to the next topic, electric power. Power is the rate of doing work. Similarly, electrical power is the electrical work done per unit time. Electrical work done per unit time. Electric power is also defined as the rate at which electrical energy is consumed. The SI unit of electric power is watt. 1 watt power. If 1 joule of work is done per second, then the electric power is 1 watt. 1 watt is equal to 1 joule upon 1 second. Kilowatt is the unit which is used for commercial purpose, and 1 kilowatt is equal to 1000 watt. Formula for calculating electric power. Power is equal to work upon time. P is equal to W upon T, but W is equal to VIT joules. Therefore, P is equal to VIT upon T. Therefore, P is equal to VI. Thus we get electric power is equal to voltage into current. Using Ohm's law, we can get P is equal to VI is equal to I square R is equal to V square upon R. The commercial unit of electric energy is kilowatt hour, commonly known as unit. Kilowatt hour is equal to 1000 watt into 3600 second is equal to 3.6 into 10 raised to 6 watt second. Therefore, 1 kilowatt hour is equal to 3.6 into 10 raised to 6 joule. Well, that ends the chapter. Hope it was a joyful learning. You have the options to view a mind map for a quick recap and a question and answer section to study the exercises. Wish you all the best. Bye till we meet again.